So is it true that any set A unioned with the empty set that that's gonna be the same as just taking the set A? What is the empty set? Let's quickly remind ourselves what that is. The empty set is simply a set containing nothing, right? These are our squiggly brackets, they contain nothing. The set A could be empty, or it could be having like 1 in it, or it could have 1 and 2, so on and so forth. This could be our A, but the empty set has to be empty. So is it true that when we're looking at the union of the two, you're just going to get the set A? And the answer is yes, this is true. And how do we know this? Let's try and draw it, right? Let's take this blob to be A, right? And then you cannot actually draw the empty set. There is no empty set. There's nothing in it. You can't draw it. So when we're taking everything in A, and then we're taking everything in nothing, that's basically what the empty set is. It's nothing. You're just going to get A, right? All you're left is shading in A. So yeah, that's the answer you're going to end up getting. But what if A has nothing in it, right? What if A, in fact, is in fact empty, just like the empty set? Well, of course, if A has nothing in it, and then the empty set has nothing in it, then the two things they have together is just going to be the empty set. There's going to be nothing in it, so that's just going to equal A. If this is our A, that's our empty set. We want to look at the union of these two things. Well, together, all they have is the same element, and that's going to be nothing. They don't have anything, so that's also still going to equal A. So how are we going to prove that this is going to be true? Well, first we have to notice it's an equivalence statement, which means that we have to prove that the left-hand side is equal to the right-hand side, and the right-hand side is equal to the left-hand side. And in math, you do this by saying every element here is going to be here, and every element here is going to be there. So the left-hand side is a subset of the right-hand side and vice versa. So let me quickly write that down. There we go. These are the two things that we need to show are true to show that the statement is going to be true. So let's go ahead and do that. So this is a for all proof because we're looking at any set A. The empty set is a specific set, so we're always going to have this is a specific set, but this can be anything. So because it can be anything, it is going to be a for all proof. So we start by saying, let A be a set. We do not need to define the empty set again because it's already defined. The reader, we're going to assume, knows what the empty set is. Because this can be anything, we have to specify that that is a set. But this is given that it's already a set, so we don't need to define it. Okay, now let's go ahead and prove our first case. Okay, so how are we going to prove that A union the empty set is going to equal just A? Well, we're going to want to start by saying A union the empty set. We're going to want to end with saying that any element here, let's call the element X, is going to be also an element of just A, right? If X is a representative element of all the elements in this set, then if all the elements in this set are in this set, that means that this is going to be a subset of this, right? If X is all the elements here, and we show that X is also here, then all the elements here are there. So how do we do this? Well, we start here, as I've said, and our goal is to get here. So what can we do? We can definitely split up what it means for X to be an element of this set. It means that X must be an element of A, or X must be an element of the empty set. Okay, so from here we immediately see that from here we can just jump immediately here. But what do we notice? You cannot jump from here to here because the empty set doesn't have any elements. So actually, what we have to say here is, when we say this, because this is the empty set, it's actually not possible for X to be in the empty set. The empty set has to remain empty. So this is actually the statement we're going to show. We're going to show that when this is true, it must be that X is an A, and because the empty set is the empty set, X cannot be in the empty set, which means that when we're saying this, X actually belongs to A and only A, which means that X is an element of A. So let's put this into words. Let's first do this by creating our element X. We're going to say, suppose that there exists some element X in our set A union the empty set. Fantastic. Then this means that X is an element of A, and X is not an element of the empty set, and I'm going to put in brackets because the empty set cannot contain any elements. Fantastic. So there can't be any elements in it. This means that X is an element of A. So we can then conclude that A union the empty set is a subset of A. Fantastic. Okay, we've proven our first case. Let's go ahead and prove the second case. Okay, so how are we going to prove that the set A is a subset of A union the empty set? Well, we're going to want to start here, and we're going to do the same strategy. We're going to create an arbitrary element Y, and this Y is going to represent all of the elements in A. And we want to show that Y is also going to be an element of A union the empty set, because if Y represents all of the elements and Y is in both, that means that because Y is in both, that all the elements here in A are going to be in A union of the empty set, which means A is a subset of the empty set. So what do? Well, from here we can't really simplify or break down what it means for Y to be in A, but we can maybe more generally define what it means. So instead of breaking it down, we're going to actually expand it. We're going to build it up almost. We're going to say that this means that Y is in A and Y is definitely not in the empty set. If Y is in a set, it can't be in the empty set because the empty set cannot have any elements in it, which means that because this is true, both of these statements have to be true, right? Which means that because this whole thing is just saying that Y is in fact an element of A union the empty set. So now let's put this into words. So what are we going to do? We're going to start by creating our element. We're going to say, suppose Y is an element of A. Fantastic. Then we're going to want to break down what we did here. We're going to say, for Y to be an element of a set, we have to say that then Y is an element of that set, and Y clearly could not have been an element of the empty set. This is always going to be true. You can't have any elements in the empty set. So Y is going to be an element of A union the empty set, making A a subset of A union empty set. There we go. We've proven the second case is also true because all the elements in A are in fact in A union the empty set. That means A is a subset of A union the empty set. Great. Okay, it's a lot of words, a lot of talking. Now let's just write our very quick short conclusion. We're going to say that since A union the empty set is a subset of A, and A is a subset of A union the empty set, then A union the empty set is simply equal to A. So there we go. We've now proven that any set unionized with the empty set is just going to be the original set itself.